In the previous lecture, we have started to discuss the theory of ensemble in statistical mechanics. And in this regard, you have seen an overview or an outline of this ensemble theory. Basically, in the first lecture on this subject, we have seen the important characteristics or important features of the three important ensembles known as micro-canonical ensemble, canonical ensemble, and grand canonical ensemble. And as I have mentioned in the previous lecture, that after that introductory lecture on ensemble theory, we will see the detailed discussion on the three ensembles separately. So this is the first lecture I have started to deal with the problems of micro-canonical ensemble. So in the forthcoming few lectures, you will see the different concepts which are important for your examination purpose regarding this micro-canonical ensemble. Before starting, the first concept of micro-canonical ensemble, which is regarding the entropy, or you can say, and the meaning of entropy in statistical mechanics or macro-canonical ensemble, I would like to just revise the basic facts regarding the micro-canonical ensemble which you have seen in the first lecture. You have seen actually that the ensemble in which the system has same fixed energy, same volume, and same number of particles is known as microcanonical ensemble. And in this figure, I have just symbolically represented this microcanonical ensemble. You can say that I have mentioned the three parameters E, V, and N, and these are actually constants. These are same for all the systems, okay, or all the assemblies. Actually, if the energy of the system is prescribed in the range, let us say delta E at the value E. If you consider, let us in phase space, two energy surfaces, as I have told you in the previous lecture, and these surfaces have energy E and E plus delta E. It means you are considering an energy interval of delta E, okay. This is actually a very narrow, or you can say a very thin energy interval, okay. And in this condition, we have seen that actually in this energy range delta E, we may form a satisfactory microcanonical ensemble by taking the density equal to 0 outside of this energy range and this rho equal to constant in this energy range, okay. So except in the selected narrow range of energy delta E at E, energy density is 0. And obviously you can say that the density distribution function rho of E, density distribution function rho of E of a microcanonical ensemble is a function of energy only, and this rho is not equal to rho of t. It means it is time independent, okay. And so finally you can say that a microcanonical ensemble can be characterized by the density distribution function rho of E in this manner. That is, rho of E is equal to constant for energy in the range delta E, and this is 0 elsewhere, okay. And as I have told you that this energy density distribution function rho of E is only a function of energy, not of time, and so it is independent of time. Actually, the systems whose energies are constant are considered as isolated system, because you know in case of isolated system there will be no exchange of energy of the system with its surrounding, and so energy will remain constant. So in this way, you can say that an isolated system can be appropriately form a microcanonical ensemble. So whenever you talk about microcanonical ensemble, definitely you have to consider an isolated system. Only then the necessary condition for a microcanonical ensemble will be satisfied. Okay. Now, the in fact, when we consider the volume of phase space where rho of E is constant, that is this region where rho of E is constant in this region, this is actually called the accessible region in the phase space. Okay. So these are the basic facts which we have already seen in the previous lecture. Now our aim is to discuss the first problem of microcanonical ensemble. And in this regard, first of all, we will see how we can define entropy of a system in case of microcanonical ensemble. Actually, we are talking about entropy of microcanonical ensemble, but don't forget that the result obtained for the entropy in case of microcanonical ensemble is actually a general definition of the entropy in statistical mechanics. So you can also say that we are going to deal with the problem of finding entropy in case of statistical mechanics. And in this lecture, you will see we will define actually two types of entropies: a statistical entropy of a system and thermodynamical entropy. And what is the relation between these two entropy, we will also see, and how the concept of thermodynamical entropy and the statistical entropy differ from each other, we will also see in this lecture. Okay. And for knowing the idea of entropy, we consider a closed system as a closed system, or you can say an isolated system, completely in equilibrium. And this closed system or the isolated system, you have just seen that this form a microcanonical ensemble. So you can also say that we consider a microcanonical ensembles having closed systems at fixed energy E naught. I have not written here energy by the symbol E, but I have denoted it by the symbol E naught for a specific value. Okay. And this system, this ensemble is completely in equilibrium. Okay. Now, if you consider an energy range of delta E naught, then the accessible volume in phase space is what? You have learnt in the previous lectures that in this energy range, the accessible volume in phase space, if we denote it by the symbol delta gamma, this will be simply delta Q times delta P. We have already learnt this fact in my lecture on the phase cell and quantum states earlier. Okay. Now you know that the dimensions of the product of this position coordinate and the momentum coordinate is simply equal to the dimensions of action. Okay. Dimensions of actions. So if you consider that F is the degree of freedom of our system, then this momentum time distance is for position coordinate, to the power F, this will be simply equal to action to the power F. Okay. F, as you know, this is degree of freedom. Okay. Actually, in quantum mechanics, this volume delta gamma represents the number of quantum states corresponding to the energy interval delta E naught. But how it will represent the number of quantum states, what we will have to make a change here, because this volume will have a dimension of action. But when you talk about number of quantum states, that will be dimensionless. So definitely to convert this volume into number of quantum states, we will have to do something, and what we will do, we will see later on. See here. In case of a quasi-classical system, as I have mentioned here, we convert the volume in phase space into number of quantum states. But how it is converted into number of quantum states, this is not a new thing for you. I have already discussed this fact in the previous lecture. Okay, and you know, if we convert this volume delta gamma in number of quantum states, you have to divide this volume delta q times delta p by h to the power f. How actually this result comes, you can see. You know that in phase space, the volume of each phase cell is equal to h to the power f. H to the power f. This is volume of each phase cell. And in each phase cell, the number of quantum state will be 1. So you can say that in volume h to the power f, the number of quantum states is 1. So in unit volume in phase space, number of quantum states will be 1 by h to the power f. And so the number of quantum states corresponding to the volume delta q into delta p, this will be what? This will be delta q into delta p divided by h to the power f. Okay, so I think you have understand how this delta q times delta p divided by h to the power f represents the number of quantum states corresponding to the volume delta q times delta p. Okay, and that's why I have written here the number of quantum states. But see here, the symbol has not been changed, because when you talk about classical statistics, then you will work with the expression delta gamma equal to delta q into delta p. But when we will talk in terms of quantum mechanics, then at the place of delta q times delta p, we will write delta q into delta p divided by h to the power f. So symbol for the number of quantum states has been also used like delta gamma. Okay, so I think you have understand this fact, and now after getting the value of number of quantum states in the accessible volume in energy range delta E naught, now you can see that this delta gamma is also called a statistical weight of the subsystem. Okay, now let us consider that our closed system contains a large number of non-interacting subsystems. Okay, if this is our closed system, then this has so many subsystems, and if the statistical weight or the number of quantum states corresponding to these subsystems are, let us say, delta gamma 1, delta gamma 2, and so on, then the statistical weight of the closed system will be what? Since this statistical weight is actually the measure of probability, so if you want to find the total statistical weight, or you can say that statistical weight of our closed system, then we will have simply to multiply the statistical weights of the individual subsystems, and we will have to multiply them. Okay, so you can say that this delta gamma is equal to delta gamma 1 times delta gamma 2 times delta gamma 3, and so on. And in compact form, you know, you can write that this delta gamma will be pi over I delta gamma I1, delta gamma I. Okay, here I will run from 1 to n, where n will represent the number of total number of subsystems. Okay, now let us take the natural log of this expression. When you will take natural log, this will be log delta gamma. Okay, and you know that when we will take log, then this product will change into sum, because you know log a times b is equal to log a plus log b, and this is evident from this result. It will be easily understandable. You can see when you will take log, this will be log delta gamma 1 times delta gamma 2 and so on. And so this will be simply log delta gamma 1 plus log delta gamma 2 and so on. Okay, so I have written here this log delta gamma is equal to log delta gamma 1 plus log delta gamma 2 and so on. And so in compact form, you can write that this log delta gamma is equal to summation over I log delta gamma I. Okay, and this result gives a very important physical meaning, that the logarithm of the statistical weight, when you take log of delta gamma, you can see this is just an additive quantity. Okay, delta gamma is a multiplicative property. When you want to find the total value of delta gamma, you have to multiply the delta gamma for individual subsystem. But if you want to find the logarithmic value of total value of delta gamma, you have to sum up the logarithmic value of the individual delta gamma for the different subsystem. So you can easily say that the logarithm of a statistical weight is an additive quantity. Okay, itself it is a multiplicative quantity, but its logarithm is an additive quantity. This is a very remarkable fact. Now we will try to understand the thermodynamic meaning of this delta gamma. Okay, what is the thermodynamic meaning of this delta gamma? Now we will try to understand. As you have seen that this delta gamma is only a function of energy, but there may be some external parameter which is not known here. That may be, let us say, pressure, that may be, let us say, temperature, which may affect the value of this delta gamma. So in general, we simply say that in general case, this delta gamma is a function of energy E naught and an external parameter A. This external parameter is not known here. Okay, so delta gamma I have written here is equal to delta gamma E naught A. Okay, now we take the logarithm of this delta gamma. Log delta gamma will be equal to log delta gamma of E naught A. Now to know the thermodynamical meaning of this delta gamma, we have some mathematical steps, and from that calculation we will be able to interpret this. So in this regard, first of all, let us take the differential of this log delta gamma. Okay, as you can see that this log delta gamma is a function of two independent variables E naught and A. So definitely we can find its differential by the process of partial differentiation. So you can see this differential of log delta gamma will be what? This will be partial derivative of log delta gamma with respect to E naught times dE naught plus partial derivative of log delta gamma with respect to A times dA. Okay. Now let us take this del log delta gamma by del E naught as a common factor in RHS. So in the first term only dE naught remains here, and as in the second term this del E naught is not present, so I have multiplied by this del E naught in the second term. So the second term is what? This is del E naught by del A times dA. Okay. Now as I have told you that this external parameter is not known here, but if you consider that this external parameter is coordinate, if you consider it, this is just our consideration, it is not fixed that we must consider it as a coordinate. When you will recognize this A as coordinate, then this del E naught by del A, that is partial derivative of energy with respect to coordinate, this has a dimension of force. Okay, energy, you know that force times length or coordinate, this will have actually the dimension of energy or work. So the force will have a dimension of E divided by L, that is energy divided by position coordinate. Okay, so this del E naught by del A will have a dimension of force, and so we represent it by the symbol A, and this A is actually called generalized macroscopic force acting in the direction of the coordinate A. Okay, so if we will recognize this external parameter A as coordinate, then in equation 5 the factor del E naught by del A will be replaced by this capital A, which is called generalized macroscopic force. Okay, and then we can write this equation 5 in this way. We have simply to write capital A instead of this del E naught by del A, and so that equation becomes like this. This is differential of log delta gamma is equal to del log delta gamma by del E naught times dE naught plus A dA. Okay, A dA. Now, when we study the in thermodynamics or in statistical mechanics, the entropy, we see that the change in a statistical entropy, actually a statistical entropy is denoted by the symbol sigma, and its change in statistical mechanics is defined like this: d sigma equal to 1 over tau dE naught plus A dA. If there is no external parameter present, then this A dA will be 0, and then d sigma will be simply equal to what? This is simply equal to dE naught by tau. Okay, actually this tau is called a statistical temperature. You have definitely an idea of entropy change in thermodynamics. This in thermodynamics we define the entropy change ds by dE divided by T. D divided by T. Okay, instead of T here in statistical mechanics we write tau, and this tau and T are related like this: tau is equal to K into T. Actually K into T has a dimension of energy. So when you talk about a statistical temperature, that temperature has not unit Kelvin, but it has unit of joule. Okay, where K is actually Boltzmann constant. Okay, so change in statistical entropy is defined as 1 over tau, where tau is called a statistical temperature, which is related to the thermodynamical temperature T via this relation, tau equal to K into T. Okay, and dE naught plus A dA. Now you can compare this equation 6 and equation 7. When we will compare, you can see that at the place of this sigma in equation 6 there is ln delta gamma. So comparing these two equations, we can easily say that the statistical entropy sigma is equal to ln delta gamma. Okay, this is a very important result. This is the defining equation of a statistical entropy. Okay, this is the defining equation. So you can see from this result that this sigma has no unit. So according to a statistical definition of entropy, entropy is a dimensionless quantity. It is a dimensionless quantity. But this is just like a number. But actually In thermodynamics, entropy has a proper unit, and this unit is actually joule per Kelvin, energy divided by temperature, you can see here. So actually, to make the entropy a dimensional quantity, we will have to do something else. But what we will do, we will see later on. But before that, you can also see that at the place of 1 over tau in equation 6, there is del log delta gamma by del E naught. Okay, and you know that so we can write 1 over tau equal to del E naught log delta gamma. But you have seen that log delta gamma is equal to sigma. So you can also say that this 1 by tau equal to del sigma by del E naught. Del sigma by del E naught. This is 1 by tau. This is actually the defining equation for the statistical temperature. And you should remember it, because this result will be used several times in the forthcoming lecture. Okay. So comparing equation 6 and 7, we have obtained two important results defined in equation A1 and A2. And equation A1 defines actually the statistical entropy, and equation A2 defines the statistical temperature. Okay. Actually, from this result, as I have told you, that according to this result, the entropy is a dimensionless quantity. Okay, dimensionless quantity. But if you want to make this quantity dimensional, then what we will have to do? Actually, we will have to introduce Boltzmann constant to give a unit for entropy. Okay, and for this, let us multiply this equation number 6 in both sides by the Boltzmann constant k. Okay, and so you can say when we will multiply by k, we will get the thermodynamical entropy. So thermodynamical entropy S is related to the statistical entropy sigma by this relation, S equal to k times sigma. You should remember it. This is relation between thermodynamical entropy S and the statistical entropy sigma. When you will multiply this sigma by k, you will get S, that is thermodynamical entropy. So thermodynamical entropy is equal to S equal to k log delta gamma. Okay, so this is the basic difference between the thermodynamical entropy S and the statistical entropy sigma. According to this definition, sigma is dimensionless, but S has a proper dimension of k, and this is joule per Kelvin. Joule per Kelvin. Okay. Now, as you have seen earlier, that this delta gamma in classical statistics represents the volume in phase space in a particular energy range, delta E naught. But when you talk about quantum statistics, you have to convert this volume in phase space in terms of the corresponding number of quantum states. So when these defining results for entropy will be used in classical statistics, then delta gamma will be replaced by delta Q into delta P. But if you deal the same problem in quantum statistics, you will write the same expression for entropy. But the value of delta gamma then will be written as delta Q times delta P divided by 2 pi h bar to the power f. This is the basic difference. Formula for entropy is not different, that is same, but meaning of delta gamma will change. In case of classical statistics, that means simply this accessible volume in a phase space, that is delta Q into delta P. But in case of quantum statistics, this delta gamma means delta q into delta p divided by h to the power f, and instead of h I have written 2 pi h bar, and f is the degree of freedom. Okay. So this is the basic result for entropy of a system in microcanonical ensemble. But as I have told you that this formula is not limited only to microcanonical ensemble. We have derived this result by considering microcanonical ensemble, but you can say this is the result used in statistical mechanics for entropy. So when we will talk about canonical ensemble, grand canonical ensemble, even then we will write the same expression for this entropy. Okay. Now we will see a very important property of this entropy. Actually, entropy is an extensive property, and so it is additive in nature. It means when you know the entropies of individual subsystems, then the entropy of the composite system is found to be sum of the entropies of the individual subsystems. But how? You can see this. As you have learnt that S is equal to K log delta gamma. Okay. And this log delta gamma, you have seen this is summation over I log delta gamma I. But this log delta gamma I represents the entropy of the ith subsystem. Okay. ith subsystem. So you can say that this will be K summation over sigma I, log summation over sigma I, and this will be equal to K times sigma, S equal to K times sigma. Or when you consider this K times sigma I, you can also say that this is summation Si. You can also say, and this summation Si will be equal to S. This is the total entropy of the system. So you can say that this S is equal to summation Si, or in other words you can say that sigma equal to summation sigma I. So it is clear that this entropy of a composite system is the sum of the entropies of its parts, that is its subsystems. Okay. That is in brief you can say that entropy is an additive property or additive quantity. Okay. Probability is a multiplicative property, that is delta gamma is a multiplicative property, but entropy is an additive property. Okay. So entropy in this way defined depends on the statistical weight you can see, and the precise expression for this statistical weight actually depends on the kind of system considered. So this result will be used in all the ensembles in whole statistical mechanics, but in accordance with the nature of the system, the expression for this delta gamma will change. Okay. So we will get the different result for the same system in different ensembles. When we will calculate the entropy of perfect gas in case of microcanonical ensemble, in case of canonical ensemble and grand canonical ensemble, you will see later on the expressions will be different, because the value of delta gamma will be different for different type of systems. So I think you have understand the concept of entropy in statistical mechanics. This is a very basic fundamental fact, and this will be used several times in our forthcoming lecture. Now in the first forthcoming lecture you will see a very important concept which is called Sackur-Tetrode equation, which means entropy of a perfect gas in microcanonical ensemble, and that is a very important concept. Okay. Thank you very much.